seems to be everything okay.
It's not getting any.
Just plug it
yeah,
off and on.
Maybe.
Yeah, it's in projector mode only, so I think. I don't know.
Okay, it seems like the projector got switched off, so sorry for that.
Yeah, it's a connection issue.
Oh, yeah, it's
Have you tried taking it out and plugging it back in?
yeah, I tried
Okay,
it.
so
It's not
okay,
attacking.
well then, because the projector is still on, it's
Yeah.
just not receiving the image from your laptop.
Actually, here it is showing it in the projector
Yes,
mode, so I think it's detecting the
so your
projector.
laptop is clearly detecting that there is a.
Oh,
Okay.
I got it. Yeah, so as I was saying, the added advantage of this Intel Soft 10 memory is that you can access these objects in a similar manner to the objects on RAM. So it is faster than SSDs, but obviously it is slower than the RAM. So what we do here is we use hybrid systems where we have non-volatile memory as well as the RAM, and we store some fraction of objects on the non-volatile memory while the rest of the objects are kept on the RAM. But again, we face some issues with this approach, and the main issue is that which objects should be made persistent and at what point these objects must be made persistent. All these decisions have to be taken by the programmer, and we all know how that goes. So this brings us to orthogonal persistency. In orthogonal persistency, programmers can annotate some static fields as durable roots, and all the objects which are reachable from the durable roots are made persistent by storing them on the non-volatile memory. So the programmer does not have to manually determine what objects have to be stored and manually decide when to make them persistent. It is all done automatically. And the current state of the art by Matsumoto et al. Implements a replication-based persistence model. So as you can see in the diagram here, we have a DRAM and NVM. On the DRAM side, we have two objects O and V, and the field F of object O is pointing to object V. And similarly, we are maintaining the copies on the NVM side also. And we have pointers from the volatile objects which are present on the RAM to the copies which are present in the NVM, which are denoted by the dashed lines. But again, we have some issues here. And the main issue is that Java supports multithreading. And because of this, there could be a case where we are trying to do some concurrent access, which could lead to inconsistent copies on NVM and DRAM. Let's look at one example. On the left-hand side, we have a copier thread. This thread will try to copy the objects to the NVM. On the right-hand side, we have a writer thread, which is just executing a normal put field instruction O.F is equal to V. We have also shown the code for the put field instruction there. And on the right-hand side, we have the current state of DRAM and NVM. As you can see, here we are considering the case that replica of O is absent. That is, we have not yet created the replica for object O. And the field F of object, we are trying to assign V to the field F of object O. You can see the highlighted instruction number 2, which shows the current program pointer. And what we are trying to do here is assign V to the field F of object O. And in the diagram, you can see that we have updated the pointer. Then we read O's replica. Now, as you can see, the replica of O is absent here. So O dash will be pointing to null. And because O dash will be pointing to null, we will be returning from the writer thread. Finally, we will go to the copier thread, which was executing concurrently. And the copier thread will automatically copy everything which is reachable from O. In this case, O and V both are reachable, and hence we have made the copy on the NVM side as well. Now, there is nothing wrong here, right? Now, let's look at the case 2 where the replica of O is already present. Now here, we are saying that the replica of O is already present, so we execute the copier thread first. We copy the object O on the NVM, and then we go to the writer thread. Again, we will assign V to the field F of object O on the DRAM, and then read the O's replica. Now, because we have the copier thread had created the replica for object O, we find that O dash is no longer null, and hence we make everything reachable from V persistent. So whenever there is a put fill instruction of type O.F is equal to V, and we want to add the pointer for the non-volatile in the non-volatile memory, we have to ensure that everything reachable from the right hand side also is persistent, and that's why this make persistent function will take care of that. And finally, we read the V's replica, and what we do is we basically add the pointer for the NVM copy also, and finally we again get a consistent state where object O and V both have copies on the NVM as well. And again, this is also a correct case. But what happens when the instructions are reordered? In x86 weak memory consistency model, it is possible for the instructions to get reordered. In the writer thread, we were executing instruction at line number 2 first. But what if instruction number 4 is executed first? We'll find that O does not have a replica yet on the NVM, and hence O dash is pointing to null. And then when we move to the copier thread, we'll simply make the copy for the object O on the NVM. And when we again go back to writer thread, now the instruction number 2, which was pending, is executed, and hence we add the pointer for field F of object O to the V. And then when we read the O dash, remember that this O dash was read before O's replica was created, and hence O dash is still pointing to null, due to which we return from the function, and hence we get inconsistent copies here. As you can see, on the DRAM we have O and V, but on the NVM we only have replica for O, that is O dash. And that brings us to the write barrier, which was proposed by Matsumoto et al. To fix this issue. In the writer thread, notice the code for put fill instruction. Everything is same except line number 3, where Matsumoto et al. Added an amfence instruction, which ensures that the instructions are no longer reordered. And we'll be calling this approach as writer wait approach henceforth. But the issue here is that this amfence is executed for all put fill instructions, and that generates a lot of overheads. So in this writer, the write barrier overhead comes because when you are executing a simple put fill instruction, for all put fill instruction, this barrier will be executed. Let's say your program does not have a single durable root. Even in those cases, you will be executing this amfence instruction, which is an additional overhead, and this increases the execution time of the program. You can look at the graph on the right hand side. On the x-axis we have some benchmarks. So XML, the first benchmark XML basically parses a protein database and creates object blobs which are stored in persistent data structures. And HAMT is hash array map tries, which is another popular persistent data structure. CHAMP is compressed hash array map prefix data structure, which is again a popular persistent data structure. And all the other benchmarks are the part of standard Da Capo benchmark suite. On the y-axis, we have the normalized execution time. So the execution time of writer wait approach is normalized to the standard HotSpot JVM, and we can see that in most of the cases the overhead is too large even when the durable roots are absent, and the overhead is close to 43.7%. And that brings us to the actual topic of the today's talk, that is reducing write barrier overheads for orthogonal persistence. So the main intuition behind our idea is that the frequency of copying is much lesser than the frequency of writing, because we'll be only storing fraction of objects on the non-volatile memory. And hence, if we can try to shift the overhead from writer to copier, we can get some improvements in cases where there are no durable roots. Now, that's why we shift the overhead to copier thread, and we ask the copier thread to make a handshake with all the threads, and then it will wait for some acknowledgement. And unless and until they get acknowledgement from all the other threads, the copier thread will not copy the objects to non-volatile memory. So let's look at the same example, case 3, where the writer wait approach without the mfence was creating inconsistent copies on the NVM. So again, instruction number 4 is executed first because of the reordering in x86 weak memory consistency model. We read the o.replica and find it is null because we don't have a replica yet. Then we go to the copier thread. Now the copier thread does something more involved here. We have not shown the entire code, but this is the abstract way of representing what we are doing here. So as you can see, we are the code, there is a for loop here which basically allocates memory on non-volatile memory for all the DRAM objects which are reachable from O. In this case, there is only object O and there are no other objects which are reachable from O. Hence, we'll just allocate some memory for object O on the NVM, but we won't copy the object yet. Then we'll perform a handshake with all the other threads, and the copier thread will wait here for some time until all the handshakes are acknowledged by all the other threads. Now, when we go back to the writer, thread, remember that O dash was null, and hence it will return from the writer thread, right? The O dash was read before we created the replica, and hence it was pointing to null. So writer thread will return, and then we reach the GC safe point. At the GC safe point, this writer thread will send an acknowledgement to the copier. And once this handshake is acknowledged, the copier thread can now proceed to copy the objects to the NVM. If you remember, we had just allocated the memory on the NVM and not actually copied it. This is the step where we do the actual copy. Now, notice that while we were doing this copy procedure, we have added V to the field F of object O on the DRAM side. And that's why there is a do-while loop present here, which basically ensures that all the objects which are reachable from O are copied on the NVM side. And in this manner, we get consistent copies on the NVM, and we fix the issue that was happening with the writer wait approach without mfence instruction. So does this shifting overhead to the copier benefits program that rarely make objects persistent? That is when there are no durable roots in the program. So as you can see, for the same benchmarks on the x-axis, here we have given the execution time normalized to the standard HotSpot VM. The first approach is in yellow color, the writer wait approach, and our new approach, will be calling it as copier wait approach, is shown in the red color. As you can see that there was initially with the writer wait approach, we had a 43.7% overhead, but with our newly proposed approach, we reduced the overhead by 75%. And as you can see, it is very close to the execution time of the standard HotSpot VM. So the goal here is to bring the execution time of our JVM, which supports non-volatile memory, closer to the standard hotspot JVM when there are no durable roots. And as evident, we were able to do it with minimal overheads. But what about the programs that frequently make the objects persistent? Now remember that we had shifted the overheads from writer to copier, and hence when objects are frequently copied to non-volatile memory, there will be large overheads. So we found that there was a handshake overhead of 37.9%, compared to the writer wait approach, when all the static fields are marked as durable root. But do we really need all these handshakes? So look at the program of writer thread again, where we were doing a simple put field operation. On line number 7, as I had explained before, whenever there is a put field instruction O.F is equal to V, and when we are adding pointers to the copies on NVM side, we have to first ensure that everything reachable from the right hand side is also persistent. And to ensure that, we call this make persistent function on V, which ensures that everything reachable from V has to be made persistent. Now this includes the copier code that we had seen before, and as you can see, there is a handshake operation here. But do we always need the handshake here? So look at the diagram on the right hand side, and as you can see, there is an object O which already has a replica on non-volatile memory. There is object Y which has a replica, but object V and X don't have a replica yet. So we have to copy those objects on the NVM. And we found that if all the objects reachable from the V, including V, are either thread local or persistent, then we can elide this handshake. And the reason is simple. If the object is thread local, so what is thread local? Objects which are created and which are accessible by the thread that creates it are called thread local objects, which means no other thread can access those objects. And if the object is thread local only, and because only one thread can access it, there is no need to perform handshake in those cases, as it is accessible only by one thread. Similarly, if the object is persistent, because it is already present on the NVM side, we don't have to copy it again to the NVM. And hence, we can skip the handshake in those cases also. So the condition here is that all the objects reachable from V, including V, should either be thread local or persistent. And that's why we proposed a persistent aware escape analysis. So the standard combined points to escape analysis is used to find the objects which are thread local. And we modified this standard analysis to recognize an additional special abstract object called a persistent object. Now in the standard escape analysis, if you read from a static field, we say that the read has given us an escaping object. So that's why X is pointing to a special abstract object called escape object. And if we read from the field of an escaping object, we again get an escaping object. Similarly, if we try to write to that escaping object, we say that all those objects which are written there also become escaping. And when we create a new thread object, we say that the thread object itself is escaping, and all the objects which are passed as a parameter to this thread are also escaping. But in the persistence aware escape analysis, we modified the flow function slightly. So now when we are reading from a durable root, we no longer get an escaping object, we get a persistent object. And if we are reading from the field of a persistent object, we again get a persistent object. Similarly, if we are writing to a persistent object, we will say that here in this case, y.f will be pointing to a persistent object. But for the thread creation statement, we'll still say that the thread, the T is pointing to a escaping thread object, and all the parameters passed to this thread object are escaping. So this small change affects how affects the results of our approach. So let's look at an example here. You don't have to worry about the grayed out part. The right hand side shows the object graph for the code until line number 10. As you can see on line number 10, we are doing r.tell is equal to program.assoc_list. Now notice that program.assoc_list is a durable root, and since we are reading from a durable root, if we had used escape analysis, we would say that r.tail will point to escaping object. You can see in the gray color we have shown that r.tail is pointing to escaping object. And on line number 11, when we do program.assoc_list is equal to r, we have to ensure that everything reachable from R, including R, should either be a thread local object or persistent object. But because in the object graph, we can see that escaping object is reachable from R, we do not perform handshake, we need to perform handshake here. We cannot elide it. On the other hand, if we use a persistent aware escape analysis, the read from the durable root will give us a persistent object. So now r.tail is no longer pointing to an escaping object, but a persistent object. So when we execute program.assoc_list is equal to r, we find that in the object graph, all the objects are either thread local or persistent, and hence we can elide the handshake in such cases. And by the way, this program is a very popular pattern found in persistent data structures. So was our static analysis successful in eliminating the handshakes? The answer is yes. So as you can see, we have shown here the number of handshakes per seconds for benchmarks without analysis and with static analysis. As you can see on the x-axis, some benchmarks are missing. This is because we have not added the benchmarks for whom the analysis did not terminate within the given amount of time. But for all the other benchmarks where the analysis terminated within time, we can see that many handshakes have been eliminated, especially for HAMT and CHAMP. We were able to eliminate all the handshakes. The execution time, again, this graph shows the execution time of our approach. The red part shows the execution time of copier weight approach and with static analysis. And the yellow part shows the execution time without analysis. And you can notice the white part above the bar. This white part is the overheads that we have. The execution is execution time is normalized to the writer weight approach. And as you can see, the static analysis eliminated 52% of the overheads on average. So we were able to eliminate lot of overheads using the static analysis, and copier weight is only copier weight now has only 2.4% overheads. So these are some of the related works. I'll skip them for now. And there are other topics which are covered in the paper that we have not shown in the presentation, especially how the transitive closure of object is copied on the NVM, how to handle races between copier and writer, how do we perform synchronization when multiple writers are trying to copy the same object, the correctness argument, as well as the additional overheads that we were able to eliminate using our static analysis, and the flow functions for our updated persistent aware escape analysis. This brings us to the conclusion. We shifted the overheads from the writer thread to copier thread, and we found that there was a 23% performance improvement on average when there are no durable roots. And the static analysis approach was able to eliminate 52% of the overheads when we mark all the static fields as durable, bringing the copier weight approach, the execution time of copier weight approach closer to the writer weight approach, and even better in some cases. So yeah, that's it. Thank you.
Yes, thank you very much. Are there questions? Yep.
Does the underlying persistent storage framework have a crash consistency and recovery model as well?
Sorry?
So what is the model for crash consistency and recovery of the persistent store?
Here we don't look at the recovery as such. We are more into like, are the copies on the NVM consistent with the copies on the RAM? So, I mean, there are cases possible when there are data races, and for which we use drag synchronization. Basically, we keep copying the objects until both the objects on the RAM and NVM are consistent.
Okay, what I was curious about is whether there's mechanism that supports crash consistency and recovery, so, such as logging techniques or something like that associated with the writes. that you could combine some of this work together with and maybe leverage some of the
Oh, yeah, we can do
mechanism
that,
there.
yeah.
Okay, all right, thank you.
That's orthogonal, but yeah, I guess there is a lot of work on which can improve. Yeah.
Further questions? Then one from my side. I think you covered it briefly within one bullet point, but what happens if there are multiple copiers for the same object? How do you prevent that you copy one object multiple times in the NVM?
Oh yeah, so we have added a sync compression in between. So when there are multiple copiers trying to copy the object, we basically create thread groups. So if one thread is copying that object, other threads will not copy the same object again. So there is a synchronization happening.
Okay, so but this could be, if there are really many of these objects, could be a small bottleneck, right?
There could be a small
bottleneck, so that
but in the
all these things have to be synchronized.
Yes,
globally.
but in the experiments, as we found out that there is indeed a overhead when we do the handshake for the copier weight approach. But with static analysis, we were able to reduce most of the overheads and we brought it closer to the writer weight approach.
As you have just mentioned it, the static analysis, you presented you could reduce the overhead, but not to zero obviously.
Yes.
Can you classify which of the overheads you cannot detect early on?
Yeah, so here we have not analyzed the library methods because the library methods could have different implementations on different JVMs. And when we are doing static analysis, we are analyzing them on a separate machine. So obviously there is a lot of opportunity within library methods. And in the XML benchmark, as you can see, like only half of the overheads are reduced. The other half was actually present in the library method. So yeah, there are opportunities in there also. And again, we are using a flow sensitive and context insensitive analysis here. So there is some conservative approximation because of the context insensitivity. If we can improve the precision of the analysis, we can reduce more overheads.
Okay, and maybe a mean question, and as a software engineer, I would never recommend that. What about when lots of reflection is in use? I would guess this is troublesome for you.
Yeah, so for now, this is a closed world assumption. Yeah.
I guess so much, as I said, but just was curious.
Yes.
Are there further questions? Then let's thank the speaker again.